Right, this is going to be a quick run through of some basic questions looking at the concept of limiting reactants and then how to incorporate use of this concept into calculations where you have to determine the quantity of product that can be made from a combination of two specified quantities of different reactants. So, from a balanced equation, we have the reacting ratio, which is represented by the large numbers. These tell us the number of different reactant molecules that combine together and the respective number of product molecules that can be made. So in the case of the reaction of nitrogen, N2, and hydrogen, H2, to form ammonia, NH3, one molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. This is what is going on the particle level. Now, of course, we must remember that when we are dealing with numbers in chemistry, we don't usually count the number of molecules as a raw number. We talk about it in terms of moles. So 1 mole of nitrogen gas will react with 3 moles of hydrogen gas to give us 2 moles of ammonia. Now this is nice and simple to see when we are dealing with what we would call the stoichiometric quantities of these substances, when we have the exact ratio as is in the balanced equation. But what if we have quantities that do not conform to this reacting ratio? So for example, in this box here, I have a combination of nitrogen and hydrogen. We have 2 nitrogen molecules and 8 hydrogen molecules. So that is a 1:4 ratio rather than a 1:3 ratio, as we would have in the reacting equation. So the question would be, how many ammonia molecules can be made from this quantity of reactants? In this case, the amount of ammonia that can be made is going to be limited by the number of nitrogen molecules. So our first nitrogen molecule reacts, that uses up 3 hydrogen molecules as per the stoichiometry in the reacting ratio. And when our second nitrogen molecule reacts, 3 more hydrogen molecules are used up. At this point, the reaction stops because we have run out of nitrogen. There is no more nitrogen to react. Even though there is hydrogen remaining, we can't produce any more ammonia. The nitrogen, the reactant that runs out first, is known as the limiting reactant. And the limiting reactant is very important when carrying out calculations of quantity, because the limiting reactant will determine how much product can be made. So in this case, the nitrogen molecules are completely used up, so we describe them as the limiting reactant. And as some of the hydrogen is left over, the hydrogen is described as in excess. It doesn't really matter how much hydrogen is present if it is in excess. I could have thousands of extra hydrogen molecules being present here, and we're not going to make any more ammonia because we've run out of nitrogen, which is a necessary reactant for the reaction to occur. So once we've determined that a reactant is in excess, it's actually irrelevant to any further calculation of the quantities of the product. We just pay attention to the limiting reactant. So, limiting reactant is the one that runs out first, which stops the reaction. The limiting reactant determines how much product is made. The excess reactant is the one which is not completely used up, so you have some of it remaining at the end. The quantity of the excess reagent is in excess of the required reacting ratio. So if we have a look at this particular question here, we are provided with molar quantities now instead of numbers of molecules. But this is fine because remember, moles are the chemist's way of counting the number of molecules, or the number of formula units. So the moles have to conform to the reacting ratios just as the number of molecules do. And if they don't, then we have reactants in excess and limiting reactants. So our task here is to determine how many moles of the product are made in this reaction from the quantities of reactants given. We have to compare the quantities of the reactants to the reacting ratio in the equation, and then we circle the reactant which is limiting, and we can then apply the ratio to that quantity to find the moles of the product. So for our first example, we have 10 moles of potassium and 2 moles of oxygen. Now the potassium to oxygen ratio in the equation is 4 to 1, 4K to O2. There's no number in front of the O2, so there's only one of those molecules. So 10 moles of potassium should react with a quarter as many of oxygen, which would be 2.5. 10 moles of potassium reacts with 2.5 moles of oxygen. Now, in this case, do we have 2.5 moles of oxygen? Well, no, we don't. We've only got 2 moles of oxygen. So we can say that the oxygen is going to be completely used up before all the potassium reacts. In this case, the oxygen is going to be limiting. So we're going to circle that quantity to remind ourselves that this is now the important quantity for determining the amount of product. Now, to find the amount of product, 1 mole of oxygen reacts to form 2 moles of potassium oxide per the equation. So 2 moles of oxygen should react to form 4 moles of potassium oxide. For our second question, we've got 6 moles of potassium and 4 moles of oxygen. Now, again, we've got this 4 to 1 ratio between potassium to oxygen. So if I've got 6 moles of potassium, that should react with 1.5 moles of oxygen, a quarter as much. Now, in this case, though, I have 4 moles of oxygen, which is much more than the potassium will react with. In this case, the oxygen is in excess of what we require. Therefore, the potassium is the limiting reactant. So we can circle the quantity of potassium to remind ourselves now that this is the important quantity. Now the ratio between the potassium and the product potassium oxide is 4 to 2, otherwise 2 to 1. So 6 moles in a 2 to 1 ratio will make 3 moles of potassium oxide. And then the very last question here, 0.5 moles of potassium and 0.2 moles of oxygen. So once again, we apply the ratio. 0.5 moles of potassium will react with a quarter as many moles of oxygen. So this will give us 0.125 moles of oxygen being used up by the potassium. But of course, in this case, we've got 0.2 moles of oxygen, which is greater than that. So once again, the oxygen is in excess, and the potassium is going to be completely used up before the oxygen is. So the potassium is our limiting reactant, and then we apply our 4 to 2 ratio, or our 2 to 1 ratio between potassium and potassium oxide. So 0.5 moles of potassium will react to give us 0.25 moles of potassium oxide. So the key thing to take out of this is we must remember the limiting reactant always determines how much product is made. When we have figured out which of our reactants is limiting, we then only pay attention to that reactant. So I've chosen here to circle the limiting reactant quantity to remind myself this is the one I have to pay attention to find the moles of product. Right, let's have a look at some rather more complex reactions now, more complex questions. So, in these types of questions, rather than being given the quantities immediately in moles, you will be given the quantities in mass. In some questions, you may in fact be given quantities of solution, so you would be given a volume and a concentration. The principle, broadly speaking, is the same, however. We need to work to find the moles of both reactants, compare the quantities of moles that we have to the reacting ratio, and then when we have done that, we can determine the limiting reactant and then find the moles of the product. So for this question, we got 10 grams of bromine reacting with 20 grams of potassium iodide, and we have to determine the maximum mass of iodine that can be produced. We're given here the balanced equation, Br2 plus 2Ki goes to 2Kbr plus I2. So our method. First of all, we're going to set out a table for our working with the equation on the top, mass, mR, and moles as the columns on the side. Okay, so it's going to look somewhat like that. Step number 2 is going to be to fill in the known masses, and we're going to mark an asterisk on the mass that we need to find. So in this case, we know the mass of bromine is 10 grams, we know the mass of potassium iodide is 20 grams, and we know that we want to find the mass of iodine, so we're going to put an asterisk in that box. You can see here I've actually already blanked out the boxes for the potassium bromide because I already knew that I wasn't going to be interested in this. The question does not ask us about potassium bromide. So I don't want to accidentally find that quantity and do a whole load of extra work that I don't need to. Step 3. Calculate the MR values and use moles equals mass over MR to find the reactant moles. So MR for Br2 is going to be 80 times by 2, which gives us 160. And the MR for Ki is going to be 39 plus 127, giving us 166. Note here we're not paying attention to that big 2 because that is not part of the formula. Okay, that's part of the stoichiometry, the reacting ratio. The formula is just Ki, so the relative formula mass just refers to the K and the I in the formula. Last of all, for I2, the MR is going to be 127 times by 2, which gives us 254. In this case, the little number is a formula number. It is telling me I've got 2 iodines bonded together into a molecule, so that little number is something we pay attention to in the MR calculation. Right, so we then find the moles by dividing the mass by the MR. So for bromine, we will do 10 divided by 160, which gives us 0.0625 moles. And for the potassium iodide, we've got 20 divided by 166, which gives us 0.120 moles. Okay, so we've got our moles of our 2 reactants now. This next step is going to be very similar to what we were doing in the previous exercise. So for step 4, we want to apply the reacting ratio from the equation to the moles of the first reactant to find the needed moles of the second reactant, the number of moles that would react with. So in this case, the bromine to potassium iodide is in a 1:2 reacting ratio. So 1 mole of bromine reacts with 2 moles of potassium iodide. So 0.625 moles, 0.0625 moles of bromine will react with twice as much potassium iodide, reacting with 0.125 moles of potassium iodide. Step 5, we then want to compare this needed quantity of potassium iodide to the quantity of potassium iodide that we actually have. So the quantity that we have is 0.120, and this is just a little bit less than the quantity that is needed. So we know that the potassium iodide is going to run out. We need 0.125 moles of potassium iodide, we just calculated that, but we only have 0.120. So we can say that the potassium iodide is limiting. So we're going to circle that quantity to remind us that's the limiting reactant, that's the one we're going to pay attention to. So our last step is then to apply the reacting ratio to the limiting reactant to find the product moles, and then we complete the calculation by finding the mass of the product that we're interested in by using MR times moles equals mass. Mr. Moles goes to mass. So in this case, we've got a 2-to-1 reacting ratio between Ki and I2. So we need to divide by 2 to find the moles of iodine. So 0.120 divided by 2 gives us 0.0602. Now in this case, note here, I have kept my original number, the 0.120, in my calculator. So there are more decimal digits after the 120, and that returns back in when I've divided that by 2. Okay, so I've just kept the number in the calculator, which is a good practice to do, so that I am using the unrounded number in my working. So I've got 0.0602 moles of iodine, and now all I have to do is multiply that by the MR of iodine, and I find that I can make 15 grams of iodine in this case. So that is then the end of our calculation. Let's have a look at one additional example. So in this case, we've got 10 grams of sulfur being reacted with 7 grams of aluminium, and we want to find the mass of aluminium sulfide that can be produced. So the first thing, we write in our table with space for mass in grams, MR and moles. Fill in the known masses. So we've got 10 of grams of sulfur, 7 of aluminium, and we're obviously trying to find the aluminium sulfide. It's the only thing that's left in this equation, so that's nice and simple. Then we want to find the MRs. So in this case, that's nice and simple. Sulfur, that's just going to be the AR of sulfur because the formula is S. So just one sulfur atom, 32. Remember, you ignore the big numbers in front because they're not part of the formula. They're a quantity. They're a part of the reacting ratio. So for the aluminium, similarly, that's going to be nice and simple. We've just got one aluminium atom, not bonded to anything else. So that's 27. And for Al2S3, that's the most complicated one here. So we've got 2 aluminiums plus 3 sulfurs, which gives us 150. So for our moles of sulfur, we're going to do 10 divided by 32, which gives us 0.3125 moles. And for aluminium, we're going to do 7 divided by 27, which gives us 0.259 moles. Our next step is then to take this and compare to the reacting ratio. So in this case, we've got a more tricky ratio here. 3 sulfurs reacts with 2 aluminiums. So when considering the moles of my sulfur, if I want to find how many moles of aluminium that sulfur will react with, I need to take the moles of the sulfur, 0.3125, I need to divide it by 3, and then times it by 2 to apply that 3:2 ratio. So 0.3125 moles of sulfur reacts with 0.3125 divided by 3 times by 2 equaling 0.2083 moles of aluminium. Now we compare that to the quantity that we have. We need 0.2083 moles of aluminium to react with our sulfur, but we have 0.259 moles of aluminium, which is a little bit more. So in this case, the needed quantity is less than the quantity that we have, so the quantity we have is in excess. This therefore means that if the aluminium is excess, the sulfur must be the limiting reactant. So the sulfur is what we're going to circle in this case. And then to complete the equation, we use the moles of the sulfur. Sulfur is in a 3:1 ratio with aluminium sulfide, 3 sulfurs to 1 aluminium sulfide. So again, we've got to apply that ratio. So we're going to divide by 3 in this case. So 0.3125 divided by 3 will give us 0.104 moles. And then our mass of aluminium sulfide can be found by taking the moles of aluminium sulfide and multiplying it by the MR, which will give us 15.6 grams in this case. Okay. Note here, it's interesting to see that the mass of the product that is made is not the same as the total mass of the reactants, and this is because a little bit of the aluminium is left over. The total mass of reactants is 17 grams, whereas the mass of the product that can be made is 15.6. So if you wanted to, you could actually figure out here how many grams of aluminium are left over by finding the difference between the total mass of the reactants and the mass of the product. So if we actually did that, 17 minus 15.6 gives us 1.4 grams of aluminium would be left over as excess in this case.